Alrighty, so you have submitted your homework. I will have a look at it later today, but in the interim, this is what it should have looked like. So if you have it in front of you. So oxidation in terms of electron transfer is loss. An oxidizing agent is the substance that gains electrons. Household bleach contains chlorine as an oxidizing agent. We are going to look at D a little bit more today, but if you put zinc into copper sulfate, the zinc becomes copper colored and the blue copper ions become colorless zinc. Chlorine and hydrogen peroxide are both oxidizing agents. The tincture of iodine uses iodine and ethanol because iodine is insoluble in water. Small amounts of chlorine are added to drinking water, and I couldn't find this in the book. No, I didn't give it a huge amount of time. What answer did you guys come up with? Didn't come up with either? Say it
So
again.
the oxygen in the air.
That's the only thing I could think of, because it's the phenols.
There was another example with something similar. It said about something like, I don't know.
Okay, I couldn't.
Is it not the enzyme in the apple?
It is, but it's also the oxygen in the air because, yeah, I couldn't find the answer to it. I'll go and Google again and I'll let you know. So in terms of these guys, how did we get on with them? So what's labelled is the oxidizing, is what's oxidized. So if something is oxidized, then it means this is the reducing agent. Reducing agent. Reducing agent. So the only ones where the first thing wasn't the thing that was oxidized was over here in F. So if it is oxidized, it is the reducing agent. Now only 2 people came with issues. So I'm assuming when I look...
I got issues as well.
Well, Mikey, you've got to share because you can't get over your issues if you don't talk about them. So there was nothing stopping you from getting in touch with me and me trying to help. Okay, we'll do a little bit more of this today.
So for D.
Yeah.
How does a 2Cu go to Cu2?
So all that, so when we start balancing these, you won't have the big numbers. When we do balancing of equations, you have to have the same number of elements on both sides. So this is copper, and while it's written as, if you get rid of this part, while it's written as just Cu, in reality copper is a metallic structure. It's like a solid. So while it only says 1 Cu, there are actually millions of Cu in a piece of copper. And you have a little electrons that are free to move, and that's what makes it metallic. So having the 2 here is just a balancing thing. And it's also the fact that as you go from here to here, so when we spread these apart, it will be Cu plus and S2 minus. So this is the thing that is oxidized. This is the thing that is reduced. And you've changed this from copper to copper plus 1, and you need to have 2 of them to balance out your... So this is when we do our naming from formulas or trying to work out. So this would be a 1, this would be a 2, so that's why the formula looks like this, because of the charges of the ions. Okay, we have a look at today's stuff. We see where we go. So we're going to try and eventually determine oxidation numbers of different elements in different compounds. And there are some that go with the charges on your periodic table, so it's really, really easy to do. But then there are others that you have to learn because they don't behave as they're expected. Now, I made a mistake in this. So on my book, it's page 106. In mine, and it's headed the electrochemical series. And the list that I've written, I wasn't thinking when I do it, is actually the reactivity series, which is slightly different arrangement. So this is just a list of metals, and it's arranged in order of their ability to be oxidized. So these are the list, and it can, so these two up here, the calcium and the sodium, you need to swap them. They're incorrect in yours. It's potassium, sodium, calcium in yours, so these guys need to swap. Now, the more reactive metal is going to be oxidized and the less reactive metal is going to be reduced. And this is, so the top has the most reactive, or the most easily oxidized, the bottom has the most easy to be reduced. Now, it's just an idea to know which of these things are more reactive. So I'll give you a stupid sentence for this in a second. Just have to adjust the one that's in your book. But if you think about it, silver, gold, platinum, you can dump them, keep them on your hands and dump them into things, and they won't, nothing will happen to them. Similarly with copper, we use it for our water pipes in our house, and again you can shove things through them and the copper won't corrode. Similarly, we've done group 1 where we can put potassium and sodium into water, so this is more chemical reactivity, but they are reactive, and similarly they can be oxidized. So if we say oxidation is loss of electrons, the guys up the top are really good at losing their electrons, and we know this because they're in group 1 and 2. Okay, so I'm going to flip forward, if that's okay. So again, it's the same list and you've swapped them over. So on your left hand side of your little table, the most reactive goes on the top. They're the people that are the elements that are easiest to lose. We put the least reactive at the bottom, and these guys are the easiest to gain electrons. So the top is the easiest to oxidize, which means these will be the strongest reducing agents, and the ones at the bottom will be the easiest to reduce, and they will be the strongest oxidizing agents. So in your head you keep with the oil rig, so oxidation is loss, reduction is gain, and you keep with the oxidation is an increase in oxidation number and your electrons go on the right, reduction is a decrease in oxidation number and your electrons will go on the left. You've got to keep these in your heads. Okay, I'm gonna go. So this is stupid sentence. Please come stay my Aunt Catherine Zeta in the lighthouse because she's got piles. So I should have mentioned carbon and hydrogen here. Technically they are not metals. They are non-metals, but they are capable of doing oxidation and reduction. So in the purification of zinc, they will actually put carbon coke in there because the carbon is more reactive. It will bring about oxidation of your iron. So while these guys are non-metals, they are still capable of doing redox in real life. Alrighty, so we are going to now look at this. So while we are waiting, you have this written very quickly for yourself. You're going to decide what's oxidized, what's reduced, and you're going to try and write your half equation for me. So it says it at the bottom, write your half equations, label with oxidation and reduction, use the OIR and the RDL, and ID your oxidizing agent and reducing agent. So you need to shout now if you have a question.
Miss, I don't really understand which ones are oxidizing agents and which one are reducing it. How do you tell?
So can you figure out what's oxidized and what's reduced? So this is where having oil rig, so you keep saying that to yourself, or you keep using one of these.
Is zinc oxidized and...
Correct. So the reason zinc is oxidized is because there is an increase in oxidation number. So it's going, essentially, if it's an element, they have oxidation numbers of 0. So here zinc is going from 0 to +2. That is an increase in oxidation number that is oxidized. So once you know the thing that is oxidized, that then becomes the reducing agent. So the thing that is oxidized, that loses its electrons, is the reducing agent because it brings about reduction in another thing. And then once you figured out what's oxidized, you know what is reduced. And similarly, this must be the oxidizing agent. Now I'm only putting it in shorthand. You need to write oxidizing agent as opposed to OA so that your examiner knows what you mean. Okay, so from this you have to write your half equations. So I just put OIR here and I put RDL here just to remind myself. You can put ox and red if you want, but just give yourself something your examiner will understand when they see it. But this will help you. So to write the oxidation line, I need to put my electrons on the right hand side. And to calculate the electrons, I find the difference between 0 and 2. So my electrons are going to go, so it's Zn2 plus, and the difference between 0 and 2 is 2, so there's 2 electrons here. And for copper, it's a decrease in oxidation number. My electrons go on the left hand side, so Cu2 plus 2e minus becomes Cu. Now if we were trying to balance this equation, we would be looking at this. Firstly, we look to see, do I have the same number of Cus across the line? So I do. I have the same number of zincs across the line, so I don't need to do anything for it. So when we write this equation, we are writing it for essentially one zinc atom here on this side. And I'm talking in a couple of minutes about halogens. But if we were balancing, we actually look to see, do I have the same number of electrons here? And these guys cancel each other out because this one is on the left side of the arrow, this one is on the right. So I then can rewrite my equation, which is the exact same as it is above, but this is now balanced for electrons. So anything else I want to say? So this is what's called a displacement reaction, and if we were in school, we could set it up very quickly. And what it means is because zinc comes much higher than copper in the electrochemical series, zinc will want to lose its electrons. And what it does is, so if this was our setup and we put a little piece of zinc into copper sulfate, so this is the zinc, this is the copper sulfate, it's the lovely blue color, and if you were to leave it over time, what happens is this is your after picture. So you actually end up with copper colored metal. The copper comes out of solution. So this will now be copper, and the liquid here, so while it was blue over here, here it is actually goes into colorless because now my zinc ions are in solution. So it's just called displacement because zinc displaces copper. So zinc just takes the place of copper. And we see this again when we do electrochem in Form 6. So are you guys happy for me to flip? I can see Jim, Sarah Talbot, Rachel and Juliet. So you're going to be, so if you guys nod, that is fine. Okay. Blah, 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 blah. Okay, so the only thing, and this is going to come up in the next ones we did. So when you write your equation line, So this is an oxidation line up here. When you write it, this line as is written is only for one iodine, but I have two iodines in my equation. So I need to double up my numbers of I, so you have to balance, these guys have to match, and then because I've added another iodine in here, I have to increase my electrons. This is really important when we go to start balancing large equations. So it's definitely a rule for the halogens, but it may be in a different context. So I know that there's an example of one with sulfur. Okay, so when you write your line, you're writing it for one iodine, but if there's more than one iodine, you need to balance it. So in this case, it was a double. Alrighty, so we're going to try these ones. Why are these coming in backwards? Okay, they're coming in backwards. Okay, so I've given you what these guys are if you break them up. So you're going to tell me what is oxidized, what's reduced. You're going to try the half equations. You're going to label up your oxidizing and reducing agent, and you're going to see, can you balance them? Now, for these ones, you can balance them without ever going through oxidation states. So in the question they'll give you, it will be balance using oxidation numbers or otherwise. And now you absolutely positively can do these guys without working out what's oxidized and what's reduced. I would ask you though to do it, because you can't always tell by an equation whether or not it will balance. And this is what we're practicing, so please do it. So I'm going to pause this share. So please shout if you have questions. There's big size, lads. So Gerald never made it, is what it looks like. So I currently can see Molly, Eva, Jill, Mark, Hannah. So lads, when you're done the first one, will you just give me a thumbs up and then I can judge everyone else? So the first one. When you're done, Mark, you just give me a thumbs up. Thank you, Eva. Thank you, Hannah. Thank you, Mark. Smile, Mark, it mightn't happen.
Miss,
Yeah.
I don't get how you got the displacement one. Do we have to find that?
Say it again.
The displacement thing.
Yeah.
How do you get it?
As in, how do you work out the charges? How do you work out what's oxidized and reduced?
Did I?
No, how is that your question? How do you work out what's oxidized and reduced?
No, I don't know.
So
I'm a bit lost.
So I'm going to switch my screen, my share. So for this one, the first thing that you have to do is recognize that sodium chloride is Na plus and Cl minus.
Yeah.
And so from this then we're trying to work out what's oxidized and what's reduced. So when I do this, I write the charges underneath them to help me out. And you can put these guys as 0, and today I'll explain why these are 0. So I'm looking for an increase in oxidation number. So here is going from 0 to +1. That is an increase, because if it was a number line, this is an increase, this is a decrease. So it's going from 0 to plus, this is an oxidation. It has to mean then that this has to be the reduction, and I just check it. It's going from 0 to -1, which is a decrease in oxidation number. This is reduction. Because sodium is oxidized, this is the reducing agent, because it's just opposite world, and because the chlorine is reduced, this is your oxidizing agent. So then I have to write what's called my half equations. So as I said, this is what I write down from next to my half equations, just to keep reminding myself. So the sodium, the electrons are going to go on the right hand side, and currently it is going Na plus 1 electron. My chlorine gets its electrons on the left hand side. It is going from 0 to -1, so I write 1 electron goes to Cl minus. Now this is the line that we just said on the top of page 107 in mine. I have 2 chlorines here, but I only have 1 on this side. So I have to increase this to 2, and I have to turn this into 2 electrons. Everybody with me to that point? And now I look at my electrons here, and I look at them here, and they're not the same number. So how would I get the same number of electrons on both lines? What would I have to do? Any takers? No joy? So I would have to multiply this top line by 2 to have the same number of electrons everywhere. So if I multiply it by 2, I have 2 here, and now I have 2 electrons here. And these guys now cancel each other out. So this will then be balanced. So I rewrite what I have. So 2Na plus Cl2 is equal to 2Na plus 2Cl minus, which is the same as saying 2NaCl. And that is a balanced by oxidation numbers an equation.
Miss, do you have to do it that way? Because I just balanced the equation at the top.
Okay, so that's my point. If a balancing comes up in the redox section of a question, I would really use your oxidation numbers to do it, because there are some of them that you can balance without oxidation numbers, but they're actually unbalanced in reality. When we go on to ones that are not ionic, it won't be balanced. You will get a wrong answer. So we will be doing plenty of those, but if it's ionic, you can get away with it. But if it's not ionic, and even some of the ones that use ionic compounds, so just the rule of thumb is, if they ask you to balance by oxidation numbers, balance by oxidation numbers, because you're taking a gamble, Harriet. we happy to try the second one? You guys are going to try the second one. So I'm just going to change my board. So the second one has calcium plus bromine goes to CaBr2, and this will come to calcium 2 plus and Br minus. Jill, did that answer your question?
Miss Yoda,
Yeah.
Okay, great. Mikey, go.
the last question,
Yep.
the way it was Na arrow, then the 2, then the Na, the electrons,
Yep.
and then it was Cl electrons and the arrow.
Yep.
Why is that different?
Why? Why is it written that way?
Well, like, why isn't it both like Na arrow then the electrons and then Cl arrow then the electrons?
Because it's telling you when you're writing your half equation. So I'll go back to the other half equations. So it was Na goes to Na plus 1 E minus. So what it's telling you is, this is telling you that this electron is lost, but we don't write it as a subtract electron. So for oxidation, the electron always goes on the right hand side because this is now left over, so that when the chlorine down here, so we'll just balance this up, chlorine plus 1 E minus goes to Cl minus. So essentially this electron that's lost by sodium is going to be picked up by chlorine, but we don't write it as a subtraction. So it's like when sodium turns to Na plus, this one electron is now left over and sitting in your reaction vessel, and it's going to be picked up by the chlorine.
So if the electron's negative, it's after the arrow, and it's positive, it's before the arrow.
So not quite in that way. So if you take away the electron for something, which you do in oxidizing, it is to the right of the arrow. If you are the thing that gains the electron, it goes to the left of the arrow. Okay. Okay, so now you can absolutely balance this equation without ever going near oxidation numbers, but this is what we're practicing. So I'm going to get started on 2 if that's okay, Eva. Good with you? Alrighty, so here we've said, and again I'll explain why, this is going from 0 to +2, so we just put a +2 under here and a -1 under here. So this is what is oxidized. Similarly, this is what is reduced. It's going from 0 to -1. This is our reducing agent up here, and this is our oxidizing agent here. So I'm writing my half equations. So my half equation is calcium goes to Ca2 plus, and because it's the thing that has lost electrons, our electrons go here, and it's going from 0 to 2, so that's leaving a 2 electrons loss. I'm going Br2 is going to add 2 electrons. Is that correct? So I'm going to write this as it is written. So reading the equation as it stands now, it's bromine and the difference is 0 to -1. So that is only 1 electron, and it is going to go to Br minus. And from my equation up here, I technically have 2 of them. So while this is balanced, I need to include 2 electrons here. Is there a question on that?
If it has a little number, then do you have to put then that number in front of it?
Yes, because remember these are ionic, so essentially this is what it would look like. Calcium has 2 outer shell electrons, and in reality, if you do the dot and cross for this bromine, it's gotten 1 of calcium's electrons here, and this guy will have the other in its outer shell. So there's technically 2 bromines. That's what this number here means.
Okay.
Okay.
Well, thank you.
So my 2's here are the exact same. I have 2 electrons, so these cancel. So this is balanced. So then it becomes calcium plus bromine goes to Ca2 plus 2Br minus, which in reality is CaBr2. Now we're practicing these ones, and these are relatively easy, but the SEC wouldn't be giving you something where you would have to work this part out from this. Theirs will be much more straightforward, but I have to start somewhere. So this is kind of where we start. You all start with the ionic because they're easy to figure out in terms of oxidation numbers. Okay, I am going to leave you to do the last one. If we say we come back at 9:30 then, so you get the last one done, turn off your camera, turn off your mic, go have a cup of tea, a stretch, do some press-ups. Okay, and I'm just going to mute me. Figure out where Gerald is.